So following on from the previous topic, we looked at dividing polynomials, right? More specifically, dividing linear polynomials into larger polynomials, right? And in the previous examples, they all divided exactly. So in one of the previous examples, we looked at dividing the polynomial x cubed minus 5x squared plus 8x minus 4 by x minus 2, and it divided exactly into that polynomial, right? And we got out x squared minus 3x plus 2. So how we'd write that is we could say x cubed minus 5x squared plus 8x minus 4, right, divided by x minus 2 gave us x squared minus 3x plus 2. Although another way of thinking about this is if we move this part over to the other side, so in order to remove the divide, we can just multiply both sides. We could rewrite this as x cubed minus 5x squared plus 8x minus 4 is equal to x squared minus 3x plus 2, but this time times x minus 2. So all we've done is we've just moved the division to the other side, and very importantly, we can see that this x minus 2 has now become a factor, right? One factor of the larger polynomial x cubed minus 5x squared, etc. Now, this is quite an important thing, right? So what we're saying is if we can divide one polynomial exactly by a linear factor, right? So in other words, let's call this polynomial p of x, right? It could be anything. And if we divide this polynomial by some factor, so let's call this factor x minus c, it would give us some new polynomial q of x, right? So if you want to compare this from the example above, p of x would be the large polynomial, x minus 2 would be x minus c, and the result is q of x. Right? So again, rearranging, we could write this as p of x is equal to q of x times x minus c. Now, doing standard substitution, what if we substituted in c into p of x? All right, so let's say we take p of x and instead of x, we change x to c. Right, q of x is some polynomial. It could be anything, but we're more interested in what would happen inside here. So wherever we have an x, we're going to replace with a c. And you'll notice that if we substitute c into the equation, we're going to get 0. Now that's a very important piece of information. What it tells us is that if we substitute a number into a polynomial, if it gives us a value of 0, right, we're able to determine that, well, not that number exactly, but that number is related to a factor of the polynomial. More specifically, we can say if we have some polynomial p of x, right, if we substitute in c into this polynomial, c could be any number, right, and it gives us 0, right, you can see that then x minus c was a factor. And that's one of the most important things that we can use when we're trying to solve these larger equations. Right, now this thing that we've just discovered here, this over here, is what we call the factor theorem. Okay, so again, substituting a value into a polynomial, if the value gives us an answer of 0, then that number, right, in this arrangement is a factor, x minus, so we change the sign of the number. So let's have a look at a simple example, right? If we take the equation 4x cubed minus 8x squared minus x plus 2, right? We can call this equation f of x, right? if we say, for instance, let's substitute in a value of 2, right? If we put in a value of 2, we're going to get 4 times 2 cubed minus 8 times 2 squared minus 2 plus 2, and this is going to simplify into 32 minus 32 minus 2 plus 2, which is equal to 0. So the number 2, when substituted into the equation, gives us an answer of 0. So this tells us that x minus 2, so we're going to change the sign, the linear factor is a factor of f of x, which is this large polynomial over here. Now, this idea can be extended because linear factors don't just have x minus 2. They can also be in the form of something like ax plus b, where a and b are constants. All right. So if we had to solve the constant, right, remember when we're solving quadratic equations, we make that factor equal to 0. If we had to make this equal to 0, we'd see that the solution would be x equal to minus b over a. And again, using this idea, we can say for some polynomial p of x, if we substitute in the value of b over a, so in other words, some fraction, and it gives us 0, that fraction could be a half, then ax minus b is a factor. Let's move on to some examples. Right, so here we have a question that says, show that x minus 3 is a factor of x cubed minus 6x squared plus 11x minus 6. And the first way they say is by algebraic division. So if something is a factor of, if one polynomial is a factor of another polynomial, it means that we can divide the polynomial exactly into that polynomial without getting a remainder. So just like we did in the previous lesson, we would write this as the dividend, and we'd put the divisor, the factor, over here, and we'd divide in, right? And so we'd get x squared, multiply in, so we'd get x cubed minus 3x squared, right? Subtract, so we're going to get minus 6x squared minus minus, which is going to give me minus 3x squared. Bring down the 11x. Right, x goes into minus 3x squared, will be minus 3x, multiply through, minus 3x squared. Minus 3x times minus 3 is going to give us positive 9x. Subtract, we're going to get 11x minus 9x, which will give us 2x. Bring down the 6, and x goes into 2x will be plus 2. Multiply through, 2x minus 6 gives us 0. So because we get a remainder of 0, we can prove that x minus 3 is a factor of the larger polynomial. Right, now the second method says use the factor theorem. So with the factor theorem, we need to remember that if x minus 3 is a factor, right? If x minus 3 is a factor, right? That means that when x minus 3 is equal to 0, right? Or when x is equal to 3, we should get 0 when we substitute it into the original equation. So if we say f of x is equal to x cubed minus 6x squared plus 11x minus 6, let's substitute in 3 and see what we get. So we'll get 3 cubed minus 6 times 3 squared plus 11 times 3 minus 6. That's going to give us 27 minus 54 plus 33 minus 6, which is 0. Okay, so because we get 0, we can say that x minus 3 is a factor of the larger polynomial. Okay, we can expand this idea with the example over here, right? So in the example here, we're told that 2x squared plus x minus 1 is a factor of this larger polynomial, But in the larger polynomial, we have these unknown constants, a and b. And they want us to find the values of these two constants, right? Now, if we have two unknown values, we can already determine that we're going to have to create some kind of simultaneous equation to solve them, right? Now, we were told that 2x squared plus x minus 1 is a factor of this large polynomial. But we know how to factorize this over here because this is just a quadratic. Okay, so let's take this quadratic 2x squared plus x minus 1 and let's factorize that. Okay, if we factorize that, we're going to get 2x, x, and the factors of 1 are 1 and 1, and we want to get positive 1, so we need to get plus 2 minus 1. So here we have factorized the factor into two smaller factors, okay? And these are both linear factors. And this is obviously helpful to us because using the factor theorem, we can say that when x is equal to a half, or when x is equal to minus 1, right, the equation or the polynomial should be equal to 0. Okay, so we can substitute those values in, and we can create two simultaneous equations for a and b and solve them. So let's label our large polynomial f of x. Let's call the large polynomial f of x, and we can call it 2x cubed minus x squared plus ax plus b. Okay, the first linear factor that we found was 2x minus 1, so that's going to be a half. So let's substitute in a half into this polynomial. Okay, f of a half should give us 0. Okay, so when we plug in a half into this equation, it should give us 0 based on the factor theorem. Okay, so that means 0 is equal to 2 times 1/2 cubed minus 1/2 squared plus a to the half plus b. And from here we can just sort of simplify things out. This is going to give us 0 is equal to 1/4 minus 1/4 plus a over 2 plus b, and we can simplify that further into a is equal to minus 2b. Okay, I've just multiplied the whole equation through by 2 and moved the b over to the other side. So I've solved for one of the variables, which is going to be useful when this is our first now simultaneous equation. Okay, now we can do the same thing with the other factor of x minus 1. So if I had to put in minus 1, I'll also get 0. So that means that everywhere there's an x, I put in minus 1 minus 1 squared plus a times minus 1 plus b. And I can simplify this into a is equal to b minus 3. This is my second simultaneous equation. And from here, we can solve equations, whatever method you want. We have a equal to something in both equations, so we can equate them together. If a is equal to minus 2b, and if a is also equal to b minus 3, that means that minus 2b must be equal to b minus 3. That means that minus 3b must be equal to minus 3, and b must be equal to 1. And we can use either of the two equations to solve for a. A is equal to b minus 3. Therefore, a is equal to 1 minus 3, which is equal to minus 2. So we've solved for both a and b.